Okay, this is section 5.2a. We're actually taking this section and splitting it up into 3 pieces. So we're going to take 3 days on this section. Each assignment, each day, is worth 1 homework assignment. So there's actually 3 involved in section 5.2. It's got an awful lot to it, and I have discovered that people really struggle with it if I try to teach it all in one day. It's just too much to handle. So we're splitting it up. And I will just teach it until I get to the point where tomorrow should start, and then your assignment will only cover what I've covered so far. Okay, so I'm on page 244, and we're going to go up through example 3 for today. It's plenty of information. All right, notice the core concept right at the beginning. Page 244. Y'all there? Core concept? This core concept is actually a reminder, although I don't think you've seen this stuff for quite a while. These are properties of exponents. This should not be new, although I may need to spend a bit of time on it to get you to recall it from your memory, to find it somewhere in your long-term memory someplace. What it says is this, and I'll give you a property, and then I'll give you an example. It should make good sense. The very first one is the product property, which says this: if you have something to the n, and you multiply it times that same something to the m. In other words, these bases of the exponents, the base parts have to be the same, or none of this applies. The exponents themselves are different, though, and the property says that if you're multiplying 2 things with the same base, then you add the exponents. It's not just something you memorize. It should make good sense. You should be able to recall that this is the case if you take an example. For example, if I take x to the 3rd times x to the 4th, bases are the same, exponents are different. I'm claiming that that's going to be x to the 7th. Well, if you remind yourself what this means, it's x times x times x. That's the x cubed. The x to the 4th is x times x times x times x. And look what's in between them. Big fat times. How many you got? 7. 7 x's multiplied together, which is 3 plus 4, because you got 3 of them here, 4 of them here, and they're being multiplied together. So you just stick a multiply in there, and you got 7 altogether. Does that make good sense? So when you're multiplying 2 things with the same base, you add the exponents. That should make sense based on what I just showed you. You good?
Yeah.
All right, then what do you suppose happens if I have, and I'm out of order on the core concept. I'm taking these out of order, because the next, intuitively, the next thing would be division. Multiplication and division kind of go together in my mind. They tend to undo each other. So I'm going to do that next. What do you suppose a to the n divided by a to the m is? We actually talked about this yesterday. What do you think that does? A to the n minus m. Right? Take a look at that. If I have x to the 7th over x to the 4th, that literally means this. And if you got x's all multiplied together over x's all multiplied together, they're all eligible for canceling. 1, 2, 3, 4. What are you left with? X to the 3rd, which just happens to be 7 minus 4. That makes good sense, right? And if you reverse that, just to remind you what we learned yesterday, if you have x to the 3rd over x to the 5th, that's going to be 3 of these on top and 5 on the bottom. And if you cancel, you end up with the 2 left on the bottom. Which means that 1 over x squared, if you follow what this property says, is the same thing as x to the 3 minus 5. That's what we learned yesterday. We talked about it, right? And I know you're bored right now, but I'm just reminding you of things, how it all fits together. If I now power that, if I have a to the n and I raise that to the m, this is the power rule, I get a to the n times m. So if I take a situation like that, I'm going to erase these now because I'm using up too much space. If I have something like x to the 3rd raised to the, I'm going to say 2 because I don't want to write forever. What this literally means, if you consider that first, which is what you're supposed to do, I mean, the exponent part of this, it means to take x to the 3rd times x to the 3rd. Use this thingy in here twice and multiply. That's what that means. And this is x, 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 and this is x, x, x with a big fat times in between. and you end up with 6 of them. Right? Which is 3 times 2. So when you're powering a power, when you exponent an exponent, you multiply the exponents. Now this is not in your core concept, but to me, since I went from multiplication to division, here I'm powering. What's the opposite of powering? Rooting of some kind? Well, look what happens there. You already know this too. If I have the nth root of a to the m, what do you do with these little guys, this indexing thing? You divide them. Here we multiply, here you divide them. Right? This one's a little bit more difficult to demonstrate with an example, but you'll see several of them as we go through today. But this makes good sense. If you're powering a power, you multiply. If you're rooting a power, you divide. You do the opposite because they're opposite operations. That's not in your core concept. Some of the other things that are, we've got the product, power of a power. Oh, power of a product. I gotta show you that one. So these tend to go together. This was multiplication, division goes to addition, subtraction. Powering and rooting goes to multiplication and division. I'll show you how to link all that together in your mind in just a minute here. This one isn't completely related. If I, to these over here, if I have a to the, I'm going to go ahead and write it a little different than the book. If I have a to the m and b to the n raised to the, I'm going to say p for power, I don't know. So you got 2 things multiplied inside, both raised to the same power. If this is a time sign, not a plus sign, we discussed that yesterday, but if that's a time sign, then you can use that power on both of them. It would be a to the mp times b to the np. In other words, it's this applied twice. Okay, and it doesn't matter how many things are in here. You could have 10 of these in here, and p would apply to each of them, so long as all 10 of them are being multiplied. You add a plus sign, now you got all kinds of trouble. But as long as this is a time sign, it's fine. The very same thing applies if you have a quotient. This was a product of 2 powers. If you have a quotient of 2 powers, a to the m over b to the n raised to the p, it still applies to each of them. Multiplication and division allows you to apply that to both of them separately, which ends up being a to the mp divided by b to the np. So it just applies to each separately. It's like applying this and this together with a power on it. It just, as long as this is multiplication and division, you start throwing plus signs and minus signs in there, you got all kinds of trouble, and that's not allowed, so try to get that out of your head. This is what I mean. Yesterday I told you this. If you have x plus 5 squared, that is not, remember I remember, it is not x squared plus 5 squared. That is not equal to that, because it's a plus sign. You can't apply that 2 to both of these separately when there's a plus or minus sign in there. You can if there's a times or a divide sign. You with me? Okay. I think some of you are going to sleep. Wake up. Okay, let's see what else I need to show you. Looks like the only other thing I need to show you and remind you of, I'm hoping this is just a reminder, and it's kind of in a class by itself too, is that A, I don't care what this is, anything, I don't care what this is, anything to the 0 is 1. And I showed you that yesterday. Remember when I did that 10 to the power development? We had 10 to the 3rd, 10 squared, 10, and then 10 to the 0 was 0. I mean, 1. And then we went to 1/10 after that. There's another reason why a to the 0 is 1, and it has to do with this property right here. For example, if I have x to the 5th over x to the 5th, isn't that, based on that property right there, isn't that x to the 0? And isn't anything divided by itself 1? That's further evidence that something to the 0 is 1. Because of that property. You follow? Just try to get it in your head. Anything to the 0 is 1, I don't care what it is. There are exceptions, but we're not going to run into them in this class. Okay? So a to the 0 is 1. There's a list of your properties. These are kind of combinations of these over here, but I want to show you something about these that's kind of interesting. We've been talking about order of operations a lot. Does anybody remember? Can anybody recite it?
Parentheses, exponents, multiplication, division, addition, subtraction.
Exactly, except for that's wrong. Your teachers have been telling you wrong all this time. Not entirely, not completely. I would not start order of operations, a list of order of operations. I would not start it with parentheses. I'll tell you why in just a minute. I would start it with exponents and then multiplication and division. By the way, just as a matter of trivia, do you know why this symbol is what it is? People get really, really concerned about, they're writing 3 halves like this. They go, or like this. They go, well, shouldn't it be like this? That's just a horizontal way of saying this, which is written vertically. This symbol means something over something else. It is a representation of a fraction. Anyway, just trivia. Multiplication, division, and then what? Addition, subtraction in this next row. This guy right up here, we've got multiplication and division, they tend to undo each other. We've got addition, subtraction, they tend to undo the opposite things. This guy seems to be left out in the cold all by himself. What goes with him? Roots. That's one thing that's always been left out of your list that you learned in grade school because you weren't ready to learn about roots, so they just left it off. They also added above this parentheses. And the reason why I'm not putting parentheses on here is because parentheses is an organizing thing. It's not something that is above exponenting. Exponenting is one of the biggest things you can do. Parentheses is not above that. It's an organizing tool. It says, get inside your parentheses that you've got in this big, massive problem, whatever it is. Get inside that grouping symbol and apply this to it. Inside. That's all it says. It says, focus your attention on the inside most problem and apply this to that until you got a number. Then step outside that to the next grouping symbol and apply this to the inside of that one. And then step out the whole side, outside the whole thing and apply this to that. This is the order of operations. Parentheses is merely an organizer. Do you follow what I'm saying? And to be a complete set, you should have roots go with exponents because it seems like this side is made up of things that in general make bigger and these things make smaller. In general, not all the time. And they tend to be opposites of each other. So to complete this, they should have roots on it. Now that you've seen that, I've spent a long time talking about that. I want you to look at this. When dealing with exponents, if the objective is to multiply, so this is our objective. This is the main idea. What do you do with the little guys? You come down one and add. When the objective is to divide two things and powers are involved, well, exponents are involved. What do you do with the little guys? If you're trying to divide ultimately, you come down one and subtract the little dudes. What happens if you're trying to ultimately you're trying to power an exponent? Well, you're in the exponent realm now, and now you got to, what do you do with the little guys? Well, you come down one and multiply them. What if you're trying to root something in some way or another? That's ultimately what you're trying to do. What do you do with these little guys right here? You come down one and divide them. Now, what happens if, and this is not a list of properties, but what happens if we decide to do this? If we have x to the 5th plus x to the 3rd? What if ultimately we're trying to add? What do we do with the little guys? Nothing. They're not like terms. You can't combine these. Combine is a word for addition and subtraction together in one thought. You cannot combine these because they're not alike. There's nothing you can do with this. How come? Because ultimately you're trying to add. What do you come down to? Nothing. You can't do anything with this. Pattern fails there. It's always a come down. It's always a come down. And if you're already at the bottom, you can't come down, so you're done. You can't fix this. Do you see how it all applies? If you can remember this little idea here, you've got all of these properties all set, except for you have to remember these combinations of things. But those 4 over there all relate back to this order of operations. Okay, so there's your properties. Let's apply them real quick. I won't spend too much time explaining. All right, the next one, we got 7. In example 1, I got 7 to the 4th times 7 to the 1/2. Which property am I looking at here? Which property have I got to apply? Which one? Multiplication, the first one. So what do we got to do? Add the exponents. Do you all know what 1/4 plus 1/2 is? you have enough experience with being on this planet to be able to handle fractions that simple? If you don't, just let me show you. If you get yourself into a situation where this is 3/8 and this is 2/11, that's gross. Just do the grunt work if you can't do it. So I'm going to take this simple one right here. We want to add 1/4 and 1/2, right? Now listen, your calculator, if you were to punch this in and this in and multiply them, you would get a way weird, strange decimal, which is not what we're after. We want to get an answer that is 7 raised to the something, which means you have to know this property. You have to know that you want to add these two. But if you can't add them, or it seems like a really arduous thing to have to do, because it's just make this do that, but you have to know you want to add. So you put parenthesis, 1 divided by 4, close it, add. Parenthesis, 1 divided by 2, close it, enter, and you get a decimal. But if you'll remember about your calculator, if you go to the math key right below the green one, is yours green?
Yes.
You go math, and the very first thing that shows up is frac. You hit enter, and it says, you want me to change the answer to a fraction? And you hit enter. You get the 3/4, which you knew you would get. But it changes it to a fraction for you. And so when you want to change a decimal to a fraction, you go math, enter, enter. So this is 7 to the 3/4. If you had something ugly like 3 to the 3/8 times 3 to the 2/11, like I said, that's just nasty. You have to find a common denominator and add them together and reduce the fraction if possible. Calculator can do it all at once. You just type in 3 divided by 8, close it, plus, parenthesis, 2 divided by 11, close it, enter. You get this wild, crazy decimal. You go math, oops, math, enter, enter. And you get 49/88. That's what you would have gotten if you found your common denominator and added it. It would have been horrible. So the answer, you just write 3 to the 49/88. You didn't have to do that ugliness, but you had to know to add them because you have this property. Do you understand? Okay. By the way, your calculator will always give you fractions that are improper. Like, for example, if the fraction that you wanted was 4 2/3, it will always tell you that that is 14/12 or 14/3. That's how it will report it. You're going to have to change it to this if you want it. And we hate this in algebra, so we'll never change it. It'll also reduce it for you, but it'll leave it improper. All right. A lot of talk. Moving on. See if we can go through this faster. The next one says 6 to the 1/2 times 4 to the 1/3 raised to the 2. Which property is that? I'm going to number these so you can give me a number. This property, this one, this one, this one, this one, this one, or the one that I erased, which is anything to the 0 is 1. Which property do you want to apply here?
5.
Yes, because the 4 and the 3 are both different bases, so you can't apply the product one because they have to have the same base for that to apply. And so we're going to take 4 to the 5th, no, 6 to the 1/2 raised to the 2. What's that? What are you going to do with the 1/2 and the 2? You're exponenting, I raised that. You're exponenting, you come down 1 and multiply. So what's 1/2 times 2?
5/2.
What? I'm doing the B part of example 1. Are you there?
5/2.
Huh?
Isn't it 5/2? 1/2 times 2.
Never mind. I have 6 to the 1/2 times 4 to the 1/3 squared.
Never mind.
Okay, so we're taking the 6 to the 1/2 and applying the power of 2 to it, and 1/2 times 2 is, so we just get 6. What's 4 to the 1/3 times 2? The 1/3 times 2 is 2/3. So it's 6 times 4 to the 2/3. Done. Sorry? Yeah, you don't have to radicalize or anything. Look at the end of the line for B. 6 times 4 to the 2/3. Finished. You see it? Okay, look at the C part. What property are you going to apply there?
Same one.
Same one. So what is 5 times negative 1/5? That's the first thing you got to do. The 5, which is the exponent of 4. What's that 5 times negative 1/5? Negative 1. What's 4 to the negative 1 better written?
1/4.
4 to the negative 1 is better written this way. I don't like negative exponents. You shouldn't either. They are the same, right? So that first expression whittles down to 1/4. Now we got 3 to the 5 raised to the negative 1/5. That's 3 to the
No, 1/3.
3 to the negative 1, which is
1/3.
1/3. And what are we doing to those two results? Multiplying them, which makes what? That one can be simplified to there, like you were asking about. Do you understand all that? Did you catch that? Let me show you another way we could have done it, just so that you know what your options are. We could have rewritten that thing 4 to the 5th times 3 to the 5th, 1 over that. By taking that negative 1/5, which was in the numerator, down to the denominator before we started. We could do that. You understand that? The negative 1/5 can be written downstairs as positive 1/5, then you can apply it, and you end up with 1 over 4 times 3, which is also 1/12. That's another way to handle it. Okay? So you can get rid of your negative exponents immediately if you like, but taking them where they're not. Okay, look at the next one, the D part. We have 5 over 5 to the 1/3. This always spooks people. And the reason why it does is because it doesn't look like it's, it doesn't look like all the parts are there. It is. 5 over 5 to the 1/3. Which one of the properties do you suppose we're going to apply to this? The second one, except for this guy doesn't have an exponent, or does it? It's always an understood 1. And I got the same base of 5, and it's 1 divided by the other, so I'm going to subtract. What do I get? 5 to the 2/3, done. But it's just that you have to understand that when there's not something there, it's a 1, so that you've got something to work with when you subtract. It's not a big deal, but you got to, it feels like something's missing. Okay, next one is 42 to the 1/3 over 6 to the 1/3. This one's kind of hairy. Raised to the what? Sorry? Second. Oh, just 2? Okay. What do you want to do with this one? Do you notice anything kind of tickling at your brain a little bit about that 42 and 6? They're not the same base, so you can't apply that rule to it. Does 6 and 42 have anything that we could?
7, actually.
Can you divide the 6 out of the 42, leaving a 7? Can you just do that because they've got exponents on it? Let me show you something. It's one of these properties in reverse to verify what we're about to do. This is the same thing as 6 times 7 to the 1/3, isn't it? Isn't this thingy right here, isn't that the same, using one of those properties, if you rewrite it, isn't that the same as 6 to the 1/3 times 7 to the 1/3 over 6 to the 1/3 squared? Do you see that? You see how I can write it that way? Now it's more clear that this is going to cancel, leaving you with 7 to the 1/3. Does that make sense? It's kind of weird. You have to split that 42 up and apply that 1/3 to both pieces of it. Then you can see the pieces clearly that are going to cancel. Leaves you with 7 to the 1/3 squared, which is what? So that's kind of ticklish one. That's kind of weird. You have to recognize that 42 and 6 have got something in common, and then reasonably take care of it. It's not just something that's magic. So that was a little bit weird. We okay on that one?
Yeah.
Okay. The book does it slightly differently, just so that you understand. I just now noticed that. They're also correct. If we went this direction instead, if we took that 1/3 kind of, it's not factoring, it's not that, but we took it out to the top, we could rewrite this as 42 over 6. You may like this one better. 42 over 6 to the 1/3. Because it's been applied to both of these, we can pull it back out here to the top of both, 42 over 6. You know what I mean? Using that thing in reverse. And then reduce this. That might feel a little better to you. So I have 7 to the 1/3 squared, which is 7 to the 2/3. That's another way to think about it. You can pull that 1/3 back out to be the exponent for both of them and see what you've got in a fraction. Okay, moving on. It's taking forever. Jeez, hurry up. Okay, there's one more core concept at the top of page 245. The reason I have to stay on this board is because it's the only one that's pictured in this. So I'm going to erase these properties now. Go back to your core concept if you need to see them. Or just remember your order of operations, that'll put the concept in one thought in your mind. Okay, this next one, this core concept is this. It says that if you have the square root of several things multiplied, a times b, I'm going to go ahead and extend it to c. You can put as many of these as you want, as long as it's times, not plus or minus, but as long as it's times or divide, then you can split those up as the square root of a times the square root of b times the square root of c, if you're dealing with square roots. If you're dealing with an nth root, any index, then it's the nth root of a, nth root of b, and nth root of c. You can split them up and handle each one of these separately. Is what that property is telling you. Same with division. If you have the nth root of a over the nth, well, let me try that again. If you have the nth root of a over b, again, division is the thing, not subtraction or addition. That's the nth root of a divided by the nth root of b. You can split them up and handle them each separately. Okay? Everybody clear? Those are the two properties that you're seeing there in the core concept. Now, applying them can be, like, understanding is easy. Applying them can be a little bit rough. So, the A part of example 2 says the cube root of 12 times the cube root of 18. That's like this over here. There are two different pieces. Does that mean we could write them like that if we wanted to? It does. It does. It means you can write it like that. So this thing is the very same as the cube root of 12 times 18. Yeah? Notice I did not multiply them out. Here's why. Because what you want to do now is apply, now that you've got them under one thing, what we want to do is kind of bust this up into pieces. And this time, I got to remind you of something. Do you guys all remember how to do this? How to simplify, for example, the square root of 24. Do you remember what to do to simplify that as much as possible? I'll come back to this in just a minute. I'll show you how it all links together. 24 is not a perfect square, is it? How do you simplify that? Yeah, prime factor to find all and get down as far as it'll go, factoring-wise. What do you want to start with? 6 and 4, fine. Okay, 6 is not prime. It factors into?
2 and 3.
And this factors into?
2 and 2.
And then what do? You look for pairs. Why do you look for pairs? Yeah, because every pair is a perfect square. So what we've got here, by prime factoring here, what I've done is rewritten this as 4 times 2 times 3. Well, if I apply that property right there, that's the square root of 4 times the square root of 6. That's 2. But that one can't be helped. That's what's really going on. When you're looking for pairs, you're looking for perfect squares so that you can square root those perfect squares and bring them out. Comes out as one of those because a perfect square is made up of 2. Square root of it is one of them. Square root of 4 is one of those 2's. You with me? See what's going on? So what do you suppose is going to happen when we go to simplify this one? You could, but then you'd have to prime factor it. You might as well start with this.
Oh.
Do you know what I'm saying?
Yeah.
Because if you multiply 12 times 18, you're going to get something in the hundreds. And then the first thing you're going to do, if you apply that property I just erased, you're going to start prime factoring. Well, you've already got a couple of factors. So I would suggest you don't multiply them together because you're going to have to yank it right back apart immediately. You know what I'm saying? This is already partly pulled apart into numbers that we can handle. But we've got to continue factoring. So what factors of 12 would you like to put here? Anything you want.
4 and 3.
4 and 3. We could have said 6 and 2, right? Okay, and this is?
2 and 2.
2 and 2, and let me tell you a little hint that's going to help you keep you from making mistakes. I realize that 3 is prime and you're done with that, but I suggest you bring it down anyway so that everything you're looking at is on one row because you forget to grab these guys that are tucked up in here in the tree somewhere, the branches, you know? Get to see them. How about 18? Where shall I split that up in? I heard 9 and 2 first, and then 3 and 3, and then I'm going to bring this down so they're all in one row. You with me? Okay, so what can we pull out?
3 is 3
2
and
sets
2.
of 3 and then 2 sets of
Well, does that come out to the sums of 3 because it's cubed?
You pull that 3 out and then
So you get
20
a 3 and 8.
So you're saying things are a little different because that thing in the hook is a 3 instead of a 2. Now we're looking for perfect cubes. And it takes 3 things to make a perfect cube. So we're going to have a 2 There's 3 2s, so I'm gonna bring out a 2, because that's 8, and the cube root of 8 is 2, and because that's 27, and the cube root of 27 is 3, and what's left? Nothing. So the answer is 6. Everything came out, there's no radical left. But if there were stuff left in there, you'd put it under a cube root. This tells you how many you gotta have to get 1 to come out. Because we're cube rooting now. Does that make sense? Okay.
Did John Leone and Jacob Ramsey show up?
Nope. Okay. The next one is a division one. We're going to try that division property. We got the 4th root of 80 over the 4th root of 5. Okay, so what we've got here is something that looks like this. Do you think it would help if we rewrote that like this? I mean, that's an option, right? Because equals goes backwards and forward. You have this, you could write it like this if you want. I'm going to do that and see if that helps. That'll be the 4th root of 80 over 5. That does help because that gives me a very clear fraction that I can divide. When you get really used to this, you won't bother writing it like this. You'll just say, oh, I can take 5 into 80 because you could write it like that. You can simplify this fraction. So how many times does 5 go into 80?
14.
It's
That's 16.
Preston, thank you for continuing to contribute. It's fine. Your contributions are wrong, but they're good contributions. All right, so we get 16. We get 16, and now we consider this. What's the 4th root of 16? And if you didn't know that it was 2, here's what you could do. You could say 4 times 4, 2, 2, 2, 2, and observe that that's a 4. We're looking for groups of 4, and there are 4 2s, so a 2 comes out, and there's nothing left, so it's just 2. Did you follow that? Okay. Now we're going to do ones where there are things left over. Like, for example, let's do the cube root of 135. Just take it straight up like that. Cube root of 135. For those of you that have had some experience with perfect cubes, 135 is not one of them. Still, the objective is to prime factor. What do you know for sure will go into this? 5. And how many times? 27. Ooh, that's a handy thing right there. If you recognize that as a perfect cube, you do not need to continue prime factoring because the cube root of this, which is what we're doing, is 3. If you did not recognize this as a cube, or you're just in idle mode and you're not really thinking, then you could continue. That would be 9 and 3, and this would be 3 and 3. Bring down the 3, bring down the 5. And I see there, oh yeah, I'm looking for cubes. So I take out a 3, and what I have left is a 5. He has to stay in what? A cube root. But if right here you recognized as you factored that was a perfect cube, you could automatically cube root 27 and bring that 3 out and have the 5 left if you wanted. But it has to be the cube root of it. Okay. Let's try another one. What if we did something like this, just for the sake of argument here? What if it was the cube root of 270 instead? Just so you understand what to do with leftovers. This is 2 and 135. I made this up so that it would work with this. That's 2 and 135. This is 5 and 27. So what we've got is 3, which comes out. What do we do with that 2 and 5? Do they add? Do they multiply? Do they divide? Multiply. And if you bring more than one thing out, they multiply on the outside. Okay, one of the last things we're doing, this is the last thing. So it's a good thing. We're out of time. 5th root of 7 over the 5th root of 8. This one's going to get ticklish, so pay attention if you haven't up to this point. If you've only been half thinking about things, get your full attention on this because this gets, like I said, a little bit ticklish here. 5th root of 7, 5th root. We could write that as the 5th root of 7/8, but I don't think it'll help. Because we can't simplify that fraction. 7 over 8 does not simplify. So that's a strategy, but it will short circuit pretty quick. So what's the problem with this? If you can't simplify it, we should just leave it, right? You can't. How come? You cannot have a radical left in the denominator. Now I could spend another 10 minutes and tell you why that is if you want. Grace is gone. You cannot have a radical in the denominator. Accept that as a rule. I will tell anybody that wants to know why that's a rule. It's a stupid rule, it's obsolete, it's ridiculous, however, you will be tested on it, and your professors in the future will expect you to know it. It's a dumb rule, I'll tell you right now. We still have to do it. It has not quite worked its way out of mathematics yet. So we still have to deal with it because you will be tested on it. That's my job to prepare you for those kinds of things. You cannot leave a radical symbol in the denominator. So here's what you got to do. You got to think, okay, I'm fifth rooting. Is there any groups of 5 and 8? If I prime factored 8, because it's this that's the problem. If I prime factored 8, that would be 4 times 2, which is 2 times 2 times 2, right?
Yeah.
There are not 5 things. Remember, I'm looking for 5 things to come out. I've only got 3. So now you ask yourself, how many more do I need to get them to come out? How many? 2 what?
2
2 2s. So if I multiply this bottom part, if I multiply it by, again, the fifth root of 2 times 2, which is 4, then I apply this property right here. I've got things separated here. If I multiply that 8 times that 4, I will get my 2 more 2s, won't I? So that when I'm done with this, I'm not done yet. That will equal on the bottom a 2. Because I provided myself with 2 more 2s so that I could get 5, so 1 could come out, right? But if that's what you do and that's all you do, you've changed the problem entirely. What happens when you multiply something by 1? What happens? Nothing. Doesn't change the value at all. So I am going to multiply by 1. I use the denominator to decide what I wanted to multiply this by so that I could get them all to come out and have nothing left over. But whatever decision I made there, I also have to multiply the top by that as well. So I'm really multiplying by 1 because something over itself is 1. So I'm multiplying the original problem by 1, which means I'm not changing its value. Just changing what it looks like, so it's proper. What was the question?
Oh, just the 4. Why did we have the 4 that I was writing?
We needed an extra 4 here because that provided the extra 2 2s to make 5 of them. That's why we chose 4 on the bottom. Had this been fifth root of 4, I would have chosen an 8 here.
Okay. Yeah.
I need 2 more 2s. So the decision is made by the denominator. I need 5 2s. Whatever I have that I had contribute extra here to provide myself with 5 2s, I also have to multiply the numerator by, so that I'm really multiplying by 1. You see?
Yeah.
Then I apply that property and I get the fifth root of 28. And there are no groups of 5 that I can pull out of 20 because I got a 7 and a 2 and a 2. There's not even close to 5 of anything, so that's as good as it's going to get. You can't have a radical in denominator, so you got to figure out, by prime factor, you got to figure out how many more things you need and multiply by the numerator by the same fifth root and then deal with the math. That comes out as a 2. That multiplies with 28. That's the proper form for that fraction. And if you were to find the value of the fifth root of 7 divided by the fifth root of 8 in your calculator, it would be the same as this value here. It's just that this is expressed properly. Okay. First assignment. This is called 5.2a. It's really easy to write down. It's only 13 problems. That's a happy day. Okay, so 5.2a is the section number. Put it in the upper right. 5.2, capital A or little a, I don't care. And the assignment is 3 through 27 odd. That's it. 3 through 27 odd. Okay? Tomorrow we'll take the next piece. Okay, there you go, folks. Whoever's viewing this. Bye.